day, everyone. Trust you are doing great. Welcome back to our physics class. Today we are looking at potential divider and logic gates. First of all, we'll discuss this. I'll describe to you what a divider is. The divider, that is just a circuit that we use to to bring down or minimize or reduce voltage anytime you want to power an electric motor or any electrical load. I have two circuits on the board which I will describe to you quickly. The first circuit on my left, you can see I have a battery which is the power supply. We have two resistors. I have R1, but my second resistor is a specialized type which is called light dependent resistor. This resistor that the resistance depends on the amount of light intensity that shine on it. Okay, all right. Now I have my electrical motor, which is the electrical load that is being powered. Now the idea behind this circuit is that the power supply, the battery, most of the time has a very high, output, and that output might destroy or spoil the electric motor. So I want to break it down. So what you do is you have two resistors, like I told you now, connected in series, such that the output of R2 will be what will power the motor. Okay, so but of course, we can my R2 may be any resistor, but it's better for me if I want to make this circuit to work for me like a sensor circuit. Maybe in a place where maybe you don't want outputs in the night, or output in the day. So the intensity of light will be what will determine how much resistance we get. Okay, so that's that. Now the second type, the same circuit actually, but in this case, we consider the temperature. It's in the environment or in an enclosure, in a place to determine the resistance. So we use a thermistor. A thermistor is a thermal resistor. Okay. Its resistance depends on the amount of heat energy, temperature in the environment. All right. Now, for us to understand this better, look at the graph that we have here. This graph is a graph of resistance against temperature or light intensity. For my thermistor and my LDR, the graph is very simple. It's an inverse graph, meaning that at very high temperature, I'm going to have low resistance. When light intensity is very high during the day, when there is large brightness, when there is brightness, you have low resistance. And it means when temperature is low, you can see from the graph, or at the same time in the dark, maybe in the night, you will have high resistance. So we can incorporate this anytime we decided to have a switch that maybe we're not available to turn light off or power off or power on. We just incorporate this temperature and light intensity component, and of course the job is done. Now, in terms of calculation, to determine my voltage output, very simple, just simple ratio. You can see it's my R2 for the two circuits that determine the output. So I have my R2 divided by the sum of the resistances, which of course they are in series, and multiplied by the VA. That will give me the voltage that will power. In this case, we have a bulb, but here we have an electric motor. Of course, two of them still fall into towards electric load. So that's about a divider. Quickly, let's look at logic gates. For logic gates, this is we call it a circuit that in electronics, in which you want circuit to control itself. Now we have 5 logic gates, and quickly we describe their operation. I have the NOT gate, I have the AND gate, I have the OR gate, we have the NAND and the NOR. Quickly, I want you to observe something. Look at this circuit diagram. You are supposed to be able to recall the symbols. Okay, for our NOT gate. The NOT gate is, you can see it has one input and one output. Now, NOT gate is also called an inverter. What it means that when you have output that is very high, in this case we refer to 1 as being high and 0 as being low. For logic gates, it can only read ones and zeros. It's not the opposite of this is what we refer to as the one that's variable. Okay, analog. Okay, so this is digital, as it were. Good. So for the first one, which is the inverter, once the input is high, the output is low, and the opposite is also true. Once you have low input, so the two tables also have very simple inputs. When input is high, which is 1, output is 0, and when input is low, output is 2. Very simple, straightforward. The first one is the second one is AND gate. For my AND gate, we have 2 input and 1 output. You can see we have the symbol is also, you can see that you just observe the symbol and ensure you are able to recall the symbol. We have 2 inputs, A and B, and output is A. The logic gate, please look closely. When you have low means 0, 0, because when you say AND, the 2 of them must be high for us to have output. So we have low, we have no output. We have 0, 1, we have no output, 1, 0, no output. It's only when you have high, 1, 1 that you have output, okay? That's what you get. For the OR gate, once you have one of them, the input being high, you have output. And that is expressed in the table. Low, we have low output. Low, high, we have output 1. High and low, and of course the last one is high, and we have output. The last two, NAND and NOR gate, this one they are just, you can see, NAND is not of hand. If you look closely, our hand gate, we added a NOT symbol, okay, just to show that it is opposite of the output of hand gate that give us the NAND gate. Okay, and that's why in our truth table, we introduce a column for NOT. So when you have 0, 0 as input, now if it's remember when it was hand gate, we should have 0 as an input. But because we're going to put the NAND gate now, the NOT is included, so opposite of that, opposite of this 0 will be 1. So for 0, 0, instead of you having 0 for AND, we're going to have 1. And the same way, 0, 1, don't forget, is an AND. If it's an AND gate, I'm supposed to have 2 of them being high for us to have output. So of course this will be 0, and of course the opposite of this will be 1. 1, 0, we have 0, 1, and the last which is 1, 1. 1, 1, remember this it could be confusing sometimes, but please ensure you look at it closely. 1, 1 for an AND gate is supposed to be 1. But because of the NOT that we have there, it will be 0. Alright? The last logic gate is the OR gate. Sorry, NOR gate. NOR gate is opposite of NOR, so OR. Okay, NOR is opposite of OR. Okay? Don't forget, for an OR gate, once you have one high input, you must have output. But in this case, since it's a NOR gate, we introduce a NOT to the output. So let's look at it. For low, which is 0, 0, if it's an OR gate, I'm supposed to have low, which is 0. Now, I may have 1. 0, 1, instead of me having 1 for OR gate, I'm having 0. And 1, 0, okay, 1, 0, if it's an OR gate, I should have 1, but I'm having NOT. And hand, of course, hand for an OR gate, 2 of them are even high, so I'm supposed to have 1. I'm having 0. So please ensure you look at this closely. The last time I would like you to take note is that look at our hand and our NOR. Look at this hand gate and this hand. Sorry, this NAND and hand. Look at this closely. You see, look at the output. Where we have 3 zeros, we have 3 1. It's just the opposite. The same way it goes to OR and NOR. Look at the output of our NOR gate. 1 you have. So if you, I advise that you look at it closely, and if you have any question, let me know. I wish you all the best. I'll see you some other time. Have a nice day. Bye for now.